So in this section, we will learn how to design balanced incomplete block designs. So this is a problem that this is this problem here in which we have blocks and we cannot apply all treatments to all blocks for some experimental limitations. So how can we do it in such a way that the comparisons are as balanced or as good as possible? Okay, so let's say that we have have 8 treatments, or I don't know how many, 6 treatments from A to F, and then we have 10 blocks. So a design is balanced if all treatments are applied the same number of times and all pairs of treatments appear in the same number of blocks. So for instance, let's say that we have this design, so each treatment is applied 5 times. So we have 5 A's and then we have 5 B's, so we have 2 and 3, and then you have 5 C's, 5 D's, and so on. And then each pair appears the same number of times. So for instance, we have the pair AB appear twice and the pair AC appear also twice. So in this block we have AC, and in this block we also have AC, and then all possible pairs they appear 2 times. So this design is balanced. So having balanced designs is really good, because all those considerations that we were doing before of having the same variance between comparisons. So for instance, here in this example here we saw that we could compare A with B, but the comparison was different, so the variability of that comparison was different than that between A and C, because the problem is that this design is not balanced. So A and C, that is a pair, appear once, but A and B, that is another pair, doesn't appear anytime. So the design is not balanced. And also it is not balanced because C appears twice while A and B appears only once. So if it is a balanced design, then we will not have this problem of different comparisons having different accuracies. So this is what we want to achieve. How to achieve that? So let's say that we have 6 treatments from A to F, and we have 24 units, and if we have 4 blocks, then we can check all treatments in each one of the blocks. Then this is a balanced design. So if it is possible, you should apply all treatments to all blocks, because that is the best way. It simplifies, we have seen it with the matrix is orthogonal, it simplifies the analysis. You can do it by hand, not with only a computer, and also it is balanced. All comparisons are the same, have the same variability, and so on. And this is balanced because you see all treatments appear the same number of times and all pairs appear the same number of times. So if possible, this is what you should aim. Let's say that you cannot. So you have to apply 6 treatments on 30 units, and you can only apply 5 of the treatments in each one of the treatment of the blocks. So you will have 6 blocks, you will apply 5 treatments per block, and then you try to keep symmetry some way. So in the first block we remove F, in the second block you remove E, in the third one you remove D, and so on. So this design is rather symmetric. In each one of the blocks you are removing only one, and this one treatment is different for each one of the blocks. So all these symmetry, or all this comparison between pairs will be symmetric. So it will be that they will have the same variability. And let's say that now we have 6 blocks and we can only apply 4 units or 4 treatments in each one of the blocks. So now you remove 2. So if you do some kind of cycling, again, keeping symmetry is good. So for instance, in the first one we remove AB, in the second one we remove BC, in the third one we remove CD. So you see there is a symmetry. We have a kind of omission pattern. So we have AB, so first and second, and then second and third, and then third and fourth. So keeping symmetry will keep the design balanced, and then all comparisons will have the same variability. So in general, so let's say that we have V number of treatments. These are called, in some contexts, they are called varieties. We have B blocks. We have we call Ri the number of blocks containing treatment I, and if the design is balanced, then Ri is the same for all treatments. Then K is the size of the block, and lambda I prime is the number of blocks in which the pair I prime is present. So for a balanced design, all this number of blocks is constant. So all pairs have the same number of blocks. So these designs are called VBRK lambda designs, and a balanced design must fulfill these constraints. So a BK must be equal to VR. The first equation simply states that the number of blocks times their size must be equal to the number of treatments and their repeats. And okay, so the order of one of these designs is R minus lambda. So R minus lambda, that is number of blocks containing treatment I and number of blocks containing the pairs, is the order of the design. Okay, so it turns out that not all possible designs exist. So not for all possible combinations of B, B, R, and so on are possible. So here we have a few of them for which these kind of designs exist. So let's say that you have 6 treatments, 10 blocks. Each treatment appears 5 times. There are 3 repetitions of each one of the combinations, and each one of the pairs appear twice. So this combination exists. So we can make this design. But if you make the number of blocks instead of 10, you make it 11. Now there is no balanced design with 11 blocks and these combinations of number of V, R, K, and lambda. So only a few of them exist. And another way of designing balanced incomplete block designs is by using okay, so this is a necessary condition for designing these blocks. So let's say that we have this configuration of treatments within the blocks. So we can put it like this. So block 1 is receiving treatments A, B, and C. Block 2 is receiving A, B, and D. So we construct this matrix and then we sum by rows. So we sum by rows. All the row sums have to be the same, and all the column sums have to be the same. If this is not fulfilled, this design is not balanced. But this is a necessary condition. It is not a sufficient condition. And here you have an example in which we have block 1 AC, block 2 BD, and then we repeat it. Now the sums by rows and columns are the same, but it is not balanced because the pair AC appear twice, but the AB or AD, they do not appear, so these lambdas are 0, so it is not a balanced design. Actually, this is kind of the same design that we had in here, the same design that we had before, that we said this is an incorrect design because we are confounding the blocks with the treatments. Okay, so yeah, an easy way to design experiments is by starting with an initial block and then making a kind of cyclic design. So let's see, we start with some combination. So we start with ABD and then we shift by 1. So let's say that we have 5 treatments. So A becomes, so we shift by 1, so A becomes B, B becomes C, D becomes E. And now we shift again by 1, so B becomes C, C becomes D, E, that is the last one, becomes the first one, so becomes A. And now you keep shifting, so C is D, D is E, A becomes B, and so on. So this design is balanced, and the next rotation, the next shift would be A, B, and D, but this is the first one. So you keep cycling and you keep shifting until you reach the first block. So that would give you the number of blocks that you need to have a balanced design. And another possibility is to use what are called Jordan squares. So let's say that you have 7 treatments and you need to construct blocks of size 3. So you construct a Latin square. So a Latin square is a Sudoku in which in each one of the columns and rows the treatments appear only once. So A appears only once in this row and it appears only once in this column, and the same for all treatments. And now once you have the Latin square, you take 3 columns and you take 3 columns, so these A, B, you take the ones in green. So now you have a design that is balanced and it has 3 treatments per block. So you can use these Latin squares to construct your balanced design. And if the number of treatments is large, and then we may use a different kind of designs also based on Latin squares. This design assumes that the experiment will be replicated several times, and at each replication the block composition changes. Okay, so here you would have, for instance, you have this we have 9 treatments. So in the first block we will apply, so we have this kind of Latin square. So we apply, we take the blocks from the rows of this one, and now we replicate, we change the configuration of this one, and then for instance now we do it by columns, so ADG, BEH, CFI, and then we replicate it again, and now we have a AFH, that is this. So it is like when you compute the determinant, so you take AFH, BDI, and CG, and yeah, you have all kind of combinations. So yeah, so you compute different kind of Latin squares here, and then you take the rows and columns and different combinations to make these blocks, to construct these blocks. So when you have many treatments, you may look at these kind of designs, cubic lattice designs or alpha lattice designs, and they are much more difficult to design, but they can give you balanced, incomplete block designs. And with this, we finish this section.